So this is our presentation for our senior design project. Our device that we designed and prototyped is the Smart Garage Parking Assistant, and we acronymed it Smart GPA. My name is Jennifer Castillo, and I'm the electrical engineer. Nicholas Zolo is our photonics engineer, and George Darden and Daniela Artero are our computer engineers. So what is a Smart GPA device? Smart GPA is a smart home device intended to be placed in a garage and alert drivers pulling into the garage to slow down and stop. The drivers will be alerted by light indicators that will display certain colors at a certain distance, and an LCD display that will display the distance that the vehicle is from the device. The intention is to aid the driver in avoiding collision in a tight space. The Smart GPA will also include a touchscreen LCD display that will allow users to configure, tune, and personalize the device. We'll go into more details in the later slides for that.
The motivation of this project came to mind when one of our members hit the wall of a parking spot at a UCF garage when running late to class. That person was me. Fortunately, there was no damage to the car, but getting a closed parking spot in a closed space can be difficult and risky to do, especially when you're running late to class or you're driving into a parking spot very fast. So we wanted to make a product that makes this easier by showing a distance indicator. There's so many products that already exist for parking garages, so we came into the conclusion of making a home parking garage system, and we wanted to add a convenience features for personal home environment. So we wanted to add a smart GUI display to it. So we wanted to make coming home and parking after work relaxing and more comfortable for the user.
So one of our goals of our project was to design and create a device that was simple and convenient to use for the user. For our distance sensor to accurately measure the distance of a moving car, allow the user to customize and personalize the device. And one of our other goals that we weren't able to achieve was to add more features to our smart home device.
So as for the specifications of the Smart GPA, we wanted to be able to pick up on a car pulling into the garage, so we need an operating range of about 1 to 10 feet. We want our measurement accuracy to be about less than 10 centimeters. It's not really important that it's super accurate, but it should be accurate enough to provide accurate information to the driver. For the measurement rate, we originally wanted it to be more than 20 hertz, but we found this was both overkill and not possible with our hardware. So we changed it to be greater than or equal to 8 hertz, which is still plenty to alert the driver. For the output power of the laser, we want it to be safe for the user, so less than 5 milliwatts means it's not dangerous to the eye. For output power of LEDs, we want it to be less than 15 watts in total. And for the input voltage, we want it to be less than 12 volts in total to ensure this is a low power system.
For the project block diagram, Daniela was in charge of the LED lights and using the microcontroller. Nick was in charge of the camera and the laser diodes, which in turn made the distance sensor work. George was in charge of the display using the microcontroller, and Jennifer was in charge of powering the whole system with a PCB. Now we're moving on to our subsystems and mechanisms.
Moving on to the use case diagram of the system, we have a touch display, the LED lights, the distance sensor, all in the enclosure, and then we have the vehicle that's operating. It's going to move towards or away from the device. So as it's doing that, the distance sensor subsystem takes constant distance measurements. And then the measurements are sent to the microcontroller, which changes the color of the LED lights and updates the touch display.
Here we have a comparison of the different distance sensor methods that we considered for the Smart GPA: the ultrasonic sensor, the laser time of flight sensor, the phase shift laser rangefinder, and the laser triangulation method. We eliminated the laser time of flight sensor and the phase shift laser rangefinder because they are high cost, and they also are very difficult to implement because the components have to be very precise and or very high performance. We also eliminated the ultrasonic sensor because although it's probably the best choice for our product, it's a bit too simple for a senior design project. It doesn't require any engineering design. So we went with the laser triangulation system instead because while it's doable, it still requires a significant amount of design and testing to make sure that it works properly. On this slide, I'm going to go into some of the details of our laser triangulation distance sensor. So we're doing a very basic laser triangulation system where we just have one laser diode and one camera at a set angle and distance from each other. And as an object moves throughout the operating range of our distance sensor, the laser dot will appear on the object at a different point in the camera's FOV. You can see at the close range, 1 foot, it's at the right side of the FOV, and at the far range, it's on the left side. So from this position, we can actually calculate the position of the object away from the camera using this equation here. Now, it may look like there's many variables in this equation, but a lot of these are actually constants for our given system. So once you plug in the constant values, you'll see that it's just a linear equation where we have our pixel position of the laser dot on the camera, and then from that we can calculate the final measured distance.
The goal of the image processing algorithm is to detect the laser dots as they're moving horizontally across the vehicle. So we will isolate it. We'll isolate the pixels on the image and pass that into a distance formula to receive the distance. So now let's go over how the algorithm actually works. So we start the Python program, and we have two separate programs. First, we instantiate a Pi video stream class in a separate thread or program. This allows us to separate the I/O of the camera, so we minimize the input-output latency and perform the calculations on a separate thread. So once that's done, we start a loop that starts with the Pi camera continuous module to process every frame, and we get each frame and turn it from a Python array into a NumPy array for faster calculation. Then we take that NumPy array and pass it into a C program that optimizes the calculations. So we perform a subtraction of RGB values, such as going through each pixel and seeing if the R value minus the G value minus the B value is above a certain threshold, and then that usually gives us the right laser pixel that appears on the image. And then so once we've isolated the pixel, then we can perform the distance calculation, and we loop back to the beginning of the process.
On this slide, we have pictures of some of the early testing setups for the Smart GPA's distance sensor. On the left, we have our first setup, which used these tools called helping hands to hold our laser diode and our camera in place. These things did work to hold the components in place, but they were very finicky and would move with the slightest touch. So we decided to get a holder specifically for our components made at the Creel machine shop. This holder can be seen on the right. It's made out of acrylic and it contains 2 set screws. These can be used to adjust the angle of the laser relative to the camera, as well as sub-out laser diodes when one burns out or needs to be replaced for some other reason. With this new holder, the distance sensor testing became much more streamlined and efficient.
Now let's move on to the graphical user interface, or the GUI. To build the GUI, we've chosen the PyQt5 framework, along with its GUI building tool, the Qt Designer. And the GUI is the main interface that the user can interact with to modify system settings. And to do this, we have 2 modes of operation. We have idle mode and operation mode. Idle mode is where they can modify settings, which we'll go into later. And operation mode is the mode that displays when the user is actually operating the device, such as moving towards the device or away from the device with their vehicle. Now let's move on to how the GUI actually switches between modes. So the Raspberry Pi is handling two separate processes. The first one is the camera that is continuously processing frames and checking for a new distance and sending that distance over to the GUI. So when a distance of 10 feet or however much the user has set in the GUI settings, when that distance is found, then the GUI switches from idle to operation mode and will continuously display that distance. And then after 10 seconds of not receiving any input, the GUI will switch back to idle mode from operation mode.
For our idle mode in the graphical user interface, we use the PyQt framework. The GUI will display two options to be selected from the idle mode, which is login and settings. And in settings, it has two different settings, either account or general settings. In the account settings, it controls login functionality, and it can also be disabled. And in general settings, we could change the date and the time and the different types of colors, the displays for the LED lights.
So let's talk about operation mode in a little more detail. Operation mode officially is the GUI state when the user is attempting to park, also known as operating the device. The main function is just to display a number large enough for the user to see as they're parking, and this number will be first in centimeters, such as 15, 50, 80 centimeters, but this can be changed in the idle mode settings to meters, feet, or inches. An operation mode should be large enough for the user to see from a good distance away.
For the light display system, the light display will be used to alert users when they are close to proximity to the garage wall. When the car is at approximately 10 feet away, it will display a green light. When it's approximately 3 to 4 feet away, it will start displaying a yellow light. And when it's closer to the garage wall, approximately like around 2 to 3 feet away, it will display a red light. These light system will be the green, yellow, and red will be the default setting colors, but they can be changed based on the user configuration and settings from the GUI system, where the user can change the green light to whatever color they want, yellow light to whatever, and so on. The closer the car gets to the garage wall, the faster the light display will blink. So when it will be a green light, it won't blink at all. When it's yellow, it will start blinking, and when it's red, it will blink a lot faster.
On this slide, we're going to go over the performance of all the subsystems of the Smart GPA. First, the distance sensor, which we were able to make work for our entire specified operating range of 1 to 10 feet, within an accuracy that is also within our specifications of plus or minus 5 centimeters. However, for some surfaces that are very dark or highly reflective, the distance sensor can miss a measurement or give an erroneous measurement. We were not able to find a solution to this problem, but thankfully it did not affect our use case very much.
For the subsystem performance of the LED lights were able to accurately quickly respond to all the distance measurements by showing the correct lighting and blinkage when the distance is 10 feet away, 3 feet away, or super close to 2 feet away from the garage wall.
Now, as for the GUI, it performs most features. It switches seamlessly between operation idle mode. It also keeps up with the distance sensor as it's calculating a value, so it displays it almost in sync. And it handles most features in the idle mode settings that we set out to have in the Senior Design 1 document. However, the account settings do not save user preferences. Right now, the account settings feature basically functions to be able to access the user settings and operation mode in the first place, but this can be disabled.
Now we're going to give a description of the components of the Smart GPA and the reasons why we chose the components that we did.
Now let's compare the microcontrollers that we were considering. We ended up with the Raspberry Pi Model 3B, but we were considering the Arduino Uno R3 clone and the MSP430 FG4618 microcontrollers. Our primary consideration was for intensive CPU power and RAM because we were processing a lot of images continuously, and this required intense CPU power. Now, the Raspberry Pi has 4-core 1.2 gigahertz CPU and 1 gigabytes of RAM versus 8 to 16 megahertz and 2 to 8 kilobytes on the other two microcontrollers. It also has support for the Pi camera and Pi display, which are easily integratable with our system, and we were not able to find any camera or display systems for the other two.
The laser diode that we chose to use for the Smart GPA's distance sensor is the high-let-go red dot laser diode. Specifically, it has a wavelength of 650 nanometers, a working voltage of 5 volts, and an output power of 5 milliwatts. This output power classifies it as a Class 3A laser, which means it's safe for skin exposure and momentary/accidental eye exposure. This fulfills our safety specifications. This laser diode in particular was chosen because it was cheap and contained a package of 10 laser diodes, so even if we burned some out during testing, we would have more to test with.
Now let's talk about the camera that we chose. It's the Raspberry Pi Camera Module V2 because of its easy integration with the Raspberry Pi. It supports a lot of resolutions and video capture as well as individual frame capture. Now the reason we chose it is because it has a library called Pi Camera that connects seamlessly with the Raspberry Pi, and it is also a low power device. Finally, moving on to the display system, we chose the Raspberry Pi 7-inch touchscreen display as it's the official touchscreen for the Raspberry Pi, so it would have easy integration. It has touchscreen capability, has a native resolution of 800 by 480 pixels, which was important to have a screen large enough for the user to interact with and see from a distance. Now the display is mounted straight onto the Raspberry Pi, so this also saves space when mounting the system all together at the end.
This shows our lighting comparison to what different types of lighting we looked at for our light display system. We looked into fiber optic lighting, non-addressable LED lights, and addressable LED lights. At the end, we chose the addressable LED WS281-2B based on the cost, input power, and the pin configurations. It cost the least amount, it had the less amount of input power, and it was easier to control. We chose the WS281-2B individually addressable LED lights, which is also called NeoPixel. The LEDs will display the specific colors and turn lights on or off depending on the distance measurements. And each LED will be individually configured and addressed in programming, which we did. The power requirements are approximately 5.5 volts and 1.67 amps per meter. We also needed a logic level converter to convert the 3.3 volts to 5.5 volts to make sure that the LED lights functioned as much as possible.
Our initial idea for the enclosure was to design an acrylic enclosure at the Crown Machine Shop where we had our distance sensor mount setup created. We didn't get that completed before the school closure and last minute decided to use a transparent plastic container as our enclosure. This actually worked well and housed almost all of our components except the distance sensor, which we have to set up externally from all our other components to get the most accurate results. In this slide we show the initial setup from my house. The distance sensor, when operational in a garage, will be below the enclosure and more lined up with a vehicle. So this was our intentional block diagram with the working PCB. Our first PCB was ordered but not manufactured. By the time all the components were obtained, we were encouraged to stay at home, and with the lack of resources, it was not possible to solder nor test our PCB. The next slide will explain how we adapted to make our project from home. I still wanted to explain our original PCB design since a lot of time was dedicated into designing and testing various components for the PCB. First, our main power supply chosen was a 6-volt rechargeable battery. We chose a battery to encourage portability of our device. The power supply would then go through a 6-volt to 5-volt step-down voltage regulator, which was added onto the PCB. The voltage regulator would then provide 5-volt power to our Raspberry Pi logic level converters and LED lights. The logic level converters were also integrated into the PCB and were used to convert the 3.3 volt output logic from the Raspberry Pi to 5 volts so that our 5-volt components such as the laser diodes and LEDs can function. The Raspberry Pi also distributed power to our Pi display, which needs 5 volts, and our Pi camera, which uses 3.3 volts. So the PCB we designed mainly consisted of power distribution and also took care of communication between components. The main subsystems on our PCB was a step-down voltage regulator and 2 logic level converters. The logic level converters were simple to design onto the board as it consisted of MOSFETs and passive elements. The voltage regulator though was more difficult to design because the components are so physically small and the current flowing through the voltage regulator required large traces. As recommended from TI, the manufacturers of the voltage regulator, a 4-layer board was designed to designate certain layers to input and output current flowing through the voltage regulator. When we were made aware of the school closure, I had already received a PCB but was missing some of the components necessary to finish soldering the board. When the PCB requirement was lifted, I decided to put the PCB aside and focus on finishing the other requirements of our project. I took the task of housing the project from my house, and it required me to be more hands-on on the other parts of the project with my teammates to achieve our device fully operating. Therefore, my process on making sure we can get the project done in a timely manner was to find a simple and quick way to power the device in my house that was normally powered from components within the senior design lab, such as the DC power supply. A piece of equipment that achieved this was the FEVOS 5-volt universal power supply. It outputs enough power to power our whole device and met requirements necessary to power nearly all of our components. This eliminated the need for a voltage regulator, which was a good thing. Granted, the voltage regulator could only work when soldered. Cannot be recreated on a breadboard. The power supply transformed the 120 volt power from a wall receptacle to the 5 volts necessary to power a device. Once I obtained this, we were able to get up to speed on working on the other parts of our project. The logic level converter was also bought online and was helpful to convert the logic voltages necessary.
Now we're going to finish off our presentation with the administrative content for the Smart GPA.
Our total budget for the project was aimed for it to be less than $500 to prototype. We have since managed to stay below budget. This chart represents how much we spent from testing phases until our final prototyping phases for each of our device components. One of our difficulties was our lack of PCB soldering skills and resources. From the beginning design process to finalizing design, and trying really hard to mitigate any risk or defects in the design that would cause the PCB not to work. A lot of time was spent fully understanding all the components and their requirements. The lack of resources ultimately is what caused our PCB not to be completed, such as testing supplies and external aid for soldering components by experts. Another difficulty in our project was figuring out the 3.3 volt logic and converting that to 5 volts for our components. It took us quite some time and delay in troubleshooting why our components were not acting right.
We also had problems with the Raspberry Pi, as it was a different flavor of Linux than we had ever used, setting up the camera, the display, and such. We also had problems with our measurement rate, the input-output latency of the camera, having to separate that from the actual calculations in a separate thread, and just figuring out that we needed to do that in the first place was a pretty big challenge. Recently, due to COVID-19 and the whole pandemic situation, we've had a problem with our display where it would no longer turn on. Maybe something happened when we were shuffling in and out of the lockers and some things like that. So we've had to resort to a HDMI display for the demonstration, as we can't replace it due to unavailability of materials.
For our work distribution, Jennifer was in charge of powering everything and making sure everything worked together. The light display, I was in charge of making sure the colors worked along with the blinking. The laser distance sensor, Nick was in charge of it, and the GUI display, George was in charge of it with all the functionalities and making sure it all worked on the display.
Unfortunately, due to the coronavirus pandemic separating our team members, we weren't able to implement many of the features that we originally wanted to add to the Smart GPA. One of these features that we wanted to implement from the very beginning was a car light detection system that used 2 photodiodes to alert the user if their car lights were left on after parking. How it would work was that one photodiode would be placed in front of the car lights, while the other would be placed above it, outside of the range of the car lights. If the photodiode placed in front of the car lights had a much larger signal than the other, then we would have reason to believe that the car lights were left on, and we would send a message to the user through SMS text message. We also plan to add additional tuning features to our GUI display, which allow you to change the internal variables of the Smart GPA and tune it properly without ever having to go into the code. However, this was canceled due to not being able to work on the GUI nearly as much as we wanted to. We also had to cancel our complete PCB and enclosure because the facilities necessary for building these ended up closing down. The toggleable camera view on the touch display was actually a feature that we planned at the beginning, but had to cancel very early on. This is because that the Python package needed for the NeoPixel LED lights was actually incompatible with the package we used for the toggleable camera view. And with that, we're at the end of the presentation. Although our group couldn't accomplish everything that we wanted to with the Smart GPA due to being separated from each other, I think that we did our best with the situation that we were handed. Thank you for watching, and have a nice day.